Yeah,
I managed.
It's a long one. But
He's an hydrologist and a senior lecturer in the Institute for Water Research in Semi-Arid, the most beautiful place in Israel.
Yeah, with no doubts.
And before that, he did a postdoc at Lancaster University in the UK, and he did his PhD also in Semi-Arid. So please take the lead from here.
Thank you, Neta. Always exciting to be here. I'm going to talk with you about a study that I conducted recently with my colleague of mine, Professor Groundwater from the Physics Department in the BGU University. We're going to talk about how we explore the relationship between climate statistics, changes in climate statistics, and their impact on groundwater recharge in semi-arid regions. I'm going to show you the water cycle that you probably all know, but I want to make sure that we talk about the same terms. So once precipitation, rain falls off the sky, it reaches to the soil surface. From there, water will evaporate back to the atmosphere, or will go to runoff, to making floods, and then or will infiltrate into the soil. Inside the soil, there is the plants will transpire some of the water, and again, they will go back to the atmosphere. And there is a small component in semi-arid areas that will go to deep drainage and eventually to groundwater systems. A groundwater system naturally will flow into the sea or will contribute water to the stream flow, but because of pumping, for example, this cycle is disturbed. Groundwater systems are super important for many communities around the world. They rely on irrigation, drinking, and industry. A lot of these communities are far away from the sea, so desalination is not always an option. Therefore, we have to make sure that we can sustainably manage this source and understand the changes, like climate changes, how they would impact the storage of groundwater. So there is a YMAP project. There is a global project that tries to classify different aquifer types, different groundwater system types. This classification is really basic, where there is major groundwater basins, complex hydrological structures, which is like the mountain aquifer, it's a karstic system, and there is local and shallow aquifers. You see that in semi-arid areas you have all of the kinds, although in Asia, in China, there are more local systems, but overall it's distributed all over the semi-arid regions. If we look at the land uses, so most of the land uses in semi-arid areas are pasture and browse for grazing, but there is a lot of areas where there is intensive agriculture activity. You can see it in India, a bit in North America, in the Sahel region in Africa, and a bit in Australia. And if we look at population density, it's quite correlated with intensive agriculture activity, where more than 1.2 billion people are concentrated in India and the Sahel region, but there are some locations in Australia and United States. And if we talk about climate projections for what will happen to groundwater storage in semi-arid areas, I took a study that was published in Nature Communication by Wu et al. In 2020. The figures on the map indicate different big groundwater systems in semi-arid locations. And they have different projections for these locations. I will only focus on two locations. One is the Middle East, which is number 3 on the map, where we see rapid decline in groundwater storage by 2100, which means that we, according to them, we're not going to have much groundwater left by the end of this century. And we see in northwestern India, where we saw the high concentrated population, there is a small decline towards the 2060s, and then rapid incline till 2100. Now, these changes are only due to natural causes, like climate change. So in northwestern India, they predict that there will be more rain. But there is a lot of uncertainty regarding these projections, and therefore we have to continue investigating. When we talk about climate or rain and evapotranspiration statistics and their changes, I want to show you a study that was done in the Sahel region, just to show you what it means, climate variability. So on the graph on your left top of the screen, the y-axis is the mean annual rainfall, and the x-axis are the years from 1950 till 2010. And what we see here from this graph that there was a decline in mean annual rainfall from 1950s till 1980s, and then a decline from 1980s till 2010. Another component of the rain that we can see is the y-axis, the plot on your right. The y-axis is like the mean number of rainy days, mean number of wet days, basically, when there was rain. And the years are from 1950 again till 2010. And we see quite a correlation between mean annual rainfall to mean number of rainy days, where there is a decline till 1980s, and then an incline again till 2010. And the last plot, and an interesting one, is in the bottom left. The y-axis there, excuse me, is the mean daily rain depth, where we see, again, a decline till the 1980s and then an incline. What is interesting about this component of the rain is that in many studies is related to emergence of runoff and floods. So it would be interesting to know if there were less floods during between the 50s to the 80s of the last century, and if there is more floods now due to the increase of this value. Another thing that is an issue in groundwater recharge is how long it takes it to arrive to the groundwater. So this is so remember, once there is rain, water reaches to the soil surface. It will take it time till it gets to groundwater. Now, there are two factors that will affect it. First is the thickness of the water zone, the unsaturated zone that is above the groundwater system, and its hydrological function that will affect the travel time of this drop of water that will reach to groundwater. There is a study by Ascott et al. 2017, also published in Nature Communication, that they show different distributions of the travel time. Basically, it will take between 20 years to 150 years in semi-arid regions for a drop of water to arrive to the groundwater system. But the problem that most of the climate records today are only spent over 50 years. Some locations you can have even 70 years. In Jerusalem, there are 100 years, but most locations with low uncertainty expand only over 50 years. Therefore, we need to generate time series of rain that are long enough, of rain and evapotranspiration, that are long enough to investigate the quantity of the groundwater recharge, the quantity of groundwater recharge, and to understand how climate variability actually affects this component. And the second thing is, once we generate the time series, we need to understand because we generate the time series according to statistics that we measured, but we need to know which statistics affect it the most and how it will affect our estimation of the groundwater recharge. So how we generate this time series of rain and evapotranspiration? The plot here, the y-axis is rain, millimeter per day, and the x-axis is 1958 till 2014 years. This is data from the CRU-TS data, which is a global daily data. I will explain it later. And first I sample I take every month, every calendar month, and I sample two empirical histograms. So the first plot on your right, the y-axis is probability, the x-axis are number of rainy days, and it's a discrete variable, right? So we have 1 wet day, 2 wet days, 3 wet days, and so on. And this is a discrete variable because I don't have a half a day. Every day that 1 millimeter was measured, and above 1 millimeter is counted as a wet day. The second, the circle empirical histogram is the daily rain depth, which is the continuous variable. It's because we measure different numbers, 11.5 a day or 12.3 millimeter a day, so this has to be a continuous variable. For the evapotranspiration time series, we basically only sample the daily evapotranspiration rates. Now we want to, again, we want to concentrate on semi-arid areas, and in semi-arid areas we have the evapotranspiration rates are quite similar at different locations in the semi-arid areas. But the temporal distribution of rain might change. So there are some locations with summer rain, and there are some locations with winter rain, and of course there is a lot of variability in between. So the y-axis on your left is the monthly evapotranspiration, and the x-axis on your right is the rainfall, the gray bars, and the black line is the evapotranspiration. And this is a site in China, Shenmu, where there is summer rain, mainly during July and August. And it should also Bedagan, where there is winter rain, as we know. And I established time series, rain and evapotranspiration time series for both locations. And this is how it looks like. This is a heavy graph, I will explain it. The top two plots are representing the mean monthly rain of the observed, it's the blue bar, and the generated time series, the red bar. And the bottom two graphs, the y-axis is the standard deviation of, again, the observed monthly rain, the monthly rain, and the red bar is the generated time series, monthly rain of the generated time series. And what I want you to notice that we have discrepancies between the values. So the observed monthly mean is a bit higher than the generated time series, and the standard deviation at the bottom is even larger. So this occurs because we don't take into account the correlation between the number of rainy days to total amount of rain that there is in the same month. We didn't take this correlation because we don't know anything about it. And we don't also take any correlation between successive months. So we don't know if January is wet, we don't know what it means about February, but sometimes it does, sometimes it doesn't. The same thing was done for the evapotranspiration time series. Again, the top two plots are for mean monthly evapotranspiration rates, and the bottom two plots are for standard deviation of ET monthly rates. And we see again the same discrepancies where the standard deviation of the observation are larger than the generated one. This is because we don't take the correlation between hot years and colder years. So there is some variability between the years and what size, and it affects the size of the evapotranspiration rates. We don't take it into account because we don't know, again, we don't know enough about it, because we have only 50 years of measurements. So we decided to correct it. So we correct it according to statistics. So in this case, I'm going to show you an example of how we corrected it to an yearly statistics. So the y-axis here is the cumulative distribution function. The x-axis is the yearly evapotranspiration rates in millimeters. The red line is the generated time series, and the blue line are the observations. And we corrected it. So the graph on the plot on the right is the correction, after the correction. And how did we correct it? We fitted the standard deviation and the mean of we fitted the generated time series to the mean and the standard deviation of the observed time series. We did it by multiplying the ratio between the standard deviation, and then we added all the differences between the mean. The function is below. If you want to understand more, I can explain to you later, but this is what we did.
How do you generate the original model time series?
So again, for the rain, I took two empirical distributions. The first empirical distribution is the number of wet days, where a wet day is 1 millimeter a day or above. And the second empirical distribution is the daily rain depth.
So you see some analytical empirical function?
It's only empirical histogram. I didn't touch any function. It's only sampling, random sampling.
So how is it wrong if it's empirical?
It's not wrong. No. There are some discrepancies because we don't take into account processes that we don't know about them, like correlation. So as we saw earlier, there is some correlation between the total amount of rain and the total number of wet days, right? But we didn't account it for because we don't know anything about it, so we kind of ignored it. But then you still know that there are some discrepancies, so you have to correct them. So we suggest to correct them by fitting to the mean and the standard deviation. So to correct the standard deviation and the mean. Because the other two momentums we can't really take into account, the sequences and the kurtosis, because we don't know enough about it because we don't know what will affect it. Right? Yeah. So for the rain, now we want to check out all these changes that we made, how it will affect our estimation of the groundwater recharge. So first of all, we created time series where we didn't change, time series of the rain that we didn't change anything. Then we did a time series where we took only the mean value of the wet days. We sampled only one empirical histogram. The third scenario was the MCDS, where we corrected the time series to the mean and standard deviation of the calendar month. So we did, for each month, we did correction. And the ACDS is the last scenario where we only corrected to the yearly mean and standard deviation. So this is how it looks like. The blue bar is observations. The y-axis are mean monthly rains. And the first one is the IES, what I told you before, the red one, that is a bit lower than the observation. The FNRD is also shows some variability. The MCDS, I think it's purple. I'm a bit colorblind. It's purple bar, and it's exactly like the observation because we corrected the mean and the standard deviation of the time series. And the ACDS is interesting because it's always higher or lower than the observations. So when we correct to the yearly statistics, there is some high variability within the month. So this is how it looks like for Shenmue and Bet Dagan on the right, Shenmue on the left. You can see the bottom two plots, the standard deviation of the monthly rain. So you see again the MCDS, the purple bar, is very similar to the observation, to the blue bar, and this is because we corrected it to these statistics. For the evapotranspiration time series, we did 6 scenarios. First, the ETDS, we didn't change anything. ETWD, this is interesting. We took the evapotranspiration, we separated for wet days and dry days. This we did because in semi-arid areas, there is it's characterized with intensive rain events. During these intensive rain events, the evapotranspiration is really low. So we thought it might affect the deep drainage component. So we took it into account, its statistics. Then we corrected the ETDS and the ETWD, we corrected to monthly statistics. And again, we corrected the ETDS and the ETW to yearly statistics. And this is how it looks like. So the observation, blue bar, the ETDS and the ETW, they are a bit lower than the observations. The ETD-SMC and the ETWD-MC, sorry about all the names, but I just want to show you that the mean is exactly the same like the observation because this is how we corrected it. And when we corrected to yearly statistics, so you can see the bars are extremely higher or lower compared to the observations, as the circle indicates. So this is how it looks like. You can see that the standard deviation of the ETD-SMC and the ETWD-MC are very similar to the observations. So in order to calculate the groundwater recharge, we need the soil hydraulic functions. So we mapped all the soils that are in the semi-arid regions around the world, and we found that 90% of the soils are composed of 4 soil types. It's clay loam, sandy clay loam, and sandy loam. You can see that loam is concentrated in Asia, and sandy clay loam is concentrated in Australia and some places in South Africa. But we decided to take the soil hydraulic functions of only of these 4 types of soils. On your right, the equations on your right are the soil hydraulic functions. This is Van Genucht and Moalem functions. On your left top, the plot represents the retention curve of the soil. This is just to show you what is the function on the right represent. And at the bottom is the Richards equation. This is how we calculate water flow in unsaturated conditions of porous media. And in order to solve the Richards equation, we have to have the soil hydraulic functions. And these are the results. Okay, so the different markers, the different symbols represent different soil types. The different colors represent the different scenarios with the evapotranspiration time series. And the x-axis will represent the scenario of the rain time series. So what we can see here, that the clay loam always produces the lowest groundwater recharge, where the sandy loam always produces the highest groundwater recharge. This result repeated for all the scenarios. It doesn't matter under summer rain or winter rain. Another issue that we can see that if we account for the statistics of the wet and dry days, if we separate evapotranspiration according to wet or dry days, or if we don't account it, it doesn't matter. We get the same recharge values. So intensive rain events, the low evapotranspiration rates during intensive rain events are not the cause for deep drainage. If we take only the mean value of the number of wet days, like I don't sample the first histogram, so I still get the same groundwater recharge, so it doesn't really affect it. And now the last 2 scenarios, the MCDS, where we correct to monthly statistics, and the ACDS, where we correct to yearly statistics, we say that if we correct the time series, the generated time series, to yearly statistics, we will always get like a really high groundwater recharge fluxes, and extremely high. And therefore, and now the last comparison is like on your left is Shenmue, all the graphs of Shenmue, and on your right, all the graphs belong to Bet Dagan. Shenmue is summer rain, Bet Dagan is winter rain, and we see that under summer rain there is, the groundwater recharge is always lower, substantially lower compared to winter rain. And what we can conclude from all these scenarios and exercise is that the way we generate a time series of rain and evapotranspiration, they are very sensitive to the statistic we choose to generate it according to. Now that we know how to generate time series, and we also know how to manipulate time series, we know how to change the statistics, so we decided to go to larger scale analysis of groundwater recharge in semi-arid locations. But in order to give credibility to this analysis, we want to find locations where groundwater recharge was estimated according to ground-based methods. Ground-based methods is like chloride mass balance or water isotopes. Someone goes and measures and then sees how much chloride stays in the ground, so therefore I know how much water actually enters the soil. So this is a paper by Moek et al. From Science of the Total Environment. He reported on 3,000 locations around the world of groundwater estimations. I extracted only points of semi-arid locations. For each point of the semi-arid location, I extracted daily climate data of the CRUTS, as I showed you at the very beginning of this lecture. Again, this is only 50 years of records, and we generated, according to our method, 400 years of time series of evapotranspiration and rain. And because one of the reviewers of the first paper said, what about soil heterogeneity? So I said, okay, let's introduce soil heterogeneity and see how it will affect groundwater recharge calculations. So I took data from, it's global data, this is like 250 pixels by Engel et al. He published the 250 in 2020. So there are 7 layers, and each layer has the soil hydraulic functions that I showed you earlier on. And I introduced them into the model. And so for each point, I ran the CRUTS climate data and introduced these soil functions. And this is what we got. So we got for 200 locations, we got quite a good similar groundwater recharge, simulated groundwater recharge compared to the reported one. So we say, okay, so for this location, we can check what would happen to groundwater recharge if we change the statistics. Okay, so this is how we change the statistics. It's with similar method as we did, as we created time series, but this time we actually, instead of like fitting to the mean, we shift it from the mean, or we shift it from the standard deviation. So the y-axis here is the probability, and the x-axis is the yearly precipitation. The blue line is the observed, the CRUTS time series. No, it's the time series that we generated from the CRUTS data. And the 2 other lines are basically the same distribution that we shifted their mean. So if we change the mean by a factor of 1.25, so you see that it shifted right. So there is more higher, for each year there is more rain, right? And if we multiply by a factor of 0.67, so we shift it to the left with this equation at the bottom. The same exercise we did for the standard deviation. Again, the y is the probability, the x is yearly precipitation in millimeters. And in this distribution, we actually changed the standard deviation. So again, the blue line is the original time series. And then when you shift the standard deviation by a factor of 0.67, so it means that there are more and more years we will have similar rain rates, where if you shift the standard deviation by a factor of 0.25, you increase the standard deviation, so we have years with more rain and years with less rain. And the same thing is for the evapotranspiration.
So when you change the mean, you change accordingly the standard deviation. I mean, we have a blue line that has, say, a red line and red line in both curves.
Well,
you do both of them simultaneously. You change the mean, you lower the mean, and you do something to increase the standard deviation, to change the standard deviation.
I actually did 4 scenarios where I changed only the mean. One scenario I changed the mean of the rain. One scenario I changed the standard deviation of the rain. And then one scenario, I changed the mean of the evapotranspiration, and then
They're both for combination.
I did each one separately. I didn't want to do it simultaneously. It's because
So there is no physical logic to lowering the mean and increasing the standard deviation, just statistical method.
the standard deviation, but the standard deviation stayed the same. We didn't touch it. It doesn't change. If you change the mean, you see here. If you change the mean, you don't change the standard deviation. Obviously, if I would change the mean really extremely, eventually I can't really do it. It's only there is a limit. But also here, when I change the standard deviation, I don't change the mean. You see, they shift around the mean. Now, I did it because today, I didn't say it at the beginning, but today climate projections, people take the climate projections that are like there are thousands of models. You input into the I don't know, Richard's equation or whatever bucket model that you've got, and then like you get an answer and you say, okay, this is what happened. This is the shift that will happen in groundwater recharge. But you don't know what actually the model, the climate model suggests. So you don't know which factor is actually affecting groundwater. So this is what we did, why we did that.
While we're on this, is there a reason why you only corrected the mean and standard deviation and not all the quantiles, like with a quantile mapping? That would be the standard kind of bias correction of the time series to do a quantile mapping.
Because what I'm sure about in my observations is the mean and the standard deviation. But you mean why I didn't change the third momentum, for example?
Yeah, all the quantiles. So doing like a standard bias correction would be the typical thing is a quantile remapping. So because then you're also assuming that your time series are normal. That the standard deviation is that your time series are normally distributed. Maybe they are, but
I'm not assuming that. It's all empirical. I don't assume anything.
You do when you calculate the standard deviation, then correcting the standard deviation, you're assuming that the time series is normally distributed.
It's implicit.
I mean, it's fine.
I don't think so.
I don't think it's probably a big deal. I was just curious why you chose this rather than quantile. Yeah.
Because any other one I know less and less. The more I go into the extreme one, I know less about them. Because there is less information in the observations. This is what you mean? If you go to more extreme quantiles, or to higher or bigger or smaller ones.
Okay, yeah, I mean, typically in like heterocline time series, the extremes really matter. So if you're not like correcting the extremes of the distribution, then sometimes that can be a problem. That's all.
Yeah, I agree with you. It can be a problem. But
especially in arid zone.
In arid zones, yeah. No, we'll talk about it later because it's an interesting question, but it's more complicated to answer.
Yeah.
All right. So this is the results we got for changing the mean of the yearly evapotranspiration. The circles indicate the different factors that we use. So we use 0.67 as I said before, 0.8, 1.05 and 1.5. We change the mean or reduce or increase the mean. And the results that we got is actually the top plot. You see that the groundwater recharge is distributed towards the left, so it means that there are more locations with higher groundwater recharge. If you look at the plot at the bottom, it's very close to the zero. It means that if I increase the mean of the yearly evapotranspiration rates, I get in most locations almost zero recharge. Now I will compare for different scenarios. Once we change the standard deviation of the evapotranspiration time series, then we change the standard deviation of the rain time series, changing the mean of the time series, and changing the mean of the evapotranspiration rates. If you look at the circle, so actually when we change the mean of the evapotranspiration rates, of the yearly evapotranspiration rates, we get much higher effect on groundwater recharge compared to changing the standard deviation of the rain or the mean of the rain or the standard deviation of the evapotranspiration rate. We see it by there is a much more values of groundwater recharge towards the higher, there are more locations with higher groundwater recharge. And again, if we change the mean of the evapotranspiration towards higher values by a factor of 1.5, has much stronger effect compared to changing the standard deviation of the rain or standard deviation of the evapotranspiration or the mean. So actually, we can say that changing the average of the evapotranspiration has the greatest effect on groundwater recharge in semi-arid regions. And then we took extreme events. We decided to do what will happen if the extreme events will double, how it will affect groundwater recharge in semi-arid regions. We did extreme events for evapotranspiration and extreme events for groundwater for rain. So we took 3 quantiles, 0.98, 0.95, and 0.9, and we doubled these events. How did we do that? We selected, we took the values, randomly values from the selected quantiles, and then we choose randomly events, normal events below these quantiles, and we replace them with the values above the quantiles. In this process, we preserve the annual mean of the evapotranspiration and of the rain, and also the number of rainy days that is conserved. It's very important. We always conserve the number of rainy days, and in this process, we also conserve the mean of the rain and the evapotranspiration. And we did 2 scenarios. Once we did it over the year. So basically, we didn't keep the seasonality. I took a quantile and randomly picked a day in the year, and I put the intensive rain, or I put the intensive evapotranspiration. And the second scenario, I did it for each month. So I basically kept the season. So I can't really have suddenly large rain events in the middle of August, if August is a dry year. And these are the results we got. The top plots is the scenario 1, is where we don't keep the seasonality, is where we choose randomly along the year an extreme event. And the bottom 2 plots represent the monthly extreme events, where we kept the seasonality and we only double the events within the month. All right? The y-axis is the fractions of locations, the locations that I chose in semi-arid locations. And the x-axis are the groundwater recharge. The colors indicate the different quantiles, where the blue line indicates the original time series, where we didn't add more extreme values. And the largest effect that we see is where we double the extreme events during throughout the year, right? We see some changes also when we change the extreme events within the month, but the largest effect is where we add more extreme rain events during the year. What is interesting to see on your right is the 2 plots represent the extreme events of evapotranspiration, and we can see that not during the year and not within the month, the effect of extreme events of evapotranspiration are actually affecting groundwater recharge, which is a bit makes sense, because even if I have a day where I have a really hot day, essentially the soil is limited to the amount of water that it actually provides to the atmosphere. So there is a limit. So even if I have a day of 10 millimeter per day, or I have a day of 15 millimeter per day, water don't really, the same amount of water will go out. So the loss is a bit, so we see that there is no really effect. I forgot about the arrow. And So now the conclusions. So as we saw, the estimation of groundwater fluxes are sensitive to the synthesis method, to the statistic I choose to generate my time series according to. And changing if the evapotranspiration rate, if the yearly evapotranspiration mean will change, we expect to see that the greatest effect on groundwater recharge compared to the other statistics. And if we change the extreme rainfall events during the year, if we'll see more and more extreme rain events throughout the year, we'll see higher groundwater fluxes. So maybe we'll see more floods, but we also will see more contribution to groundwater systems. Thank you.
Okay, questions? If you have more.
Thank you. Yeah. I have some questions. First, did you check sensitivity, not just to extreme day, I guess extreme in one day, extreme storm, for example, long storms, large amounts that we expect to have a larger effect on the nature?
Specific? Okay.
And that's also, just wait, what climatic classification did you use? You see, the design for you is semi-arid or?
Only for the, so for each location that I choose, for each study that reported groundwater recharge, so I took the coordinates, and I took according to these coordinates, I choose the CRU-TS data and the soil parameters data. So it's on a scale of 50 kilometers, around 50, depends where you are in the altitude, but it's a scale of 50 kilometers.
Okay, and the last point is, I think you said that, but typically we see that the main standard deviation are correlated. So I don't know if to change only one of them is,
Yeah.
but okay.
Well, this is a preliminary. It's because, again, I also now work on these climate projections, and I try to understand. I took like 20 models to see what each one suggests on the mean and the standard deviation. I'm sure that there is synergism. I'm sure there is like mutual effect. But first I want to understand if there is, what would be the magnitude of the effect of each one of these factors. Obviously, as this research will progress, we'll do more flexible analysis to see how it will affect groundwater recharge, and
That's the first question, if
Sure,
you can.
sure.
Long duration.
So I didn't check about the extreme values. What I did do when I initially started to generate time series, so I did try to account for, let's say, a week event or 4 days event, and now it will affect groundwater recharge. And I didn't see something that is substantially different than only randomly sample rain. Because how do I do that? I sample like the number of wet days, and then number of wet days I choose the rain depth also from empirical distribution. So if it's very wet months, so you might have like 15 days that are in a row, or 50 distributed days. Like at least some of them will be in it. So we didn't see any effect on groundwater recharge estimations. Now the question if it's, I believe that there are some locations that will be more sensitive to that. Probably sand dunes and stuff like that.
Let's continue this one, and I have another question. Maybe your summer versus winter is exactly the result of why you get more is because of duration, rather than any other aspect. You take winter storms 3, 4, 5 days versus summer storms, which are a few hours. So by definition, the duration is inside, but you avoid it. By definition, your summer versus winter is duration.
In
Storms.
Specifically in Saint-Mou, because I was there during the experiment, The rain events during summer can be 4 or 5 days. It's like a semi-arid area with with the tropic systems. So you suddenly have like 35 degrees, and the following day you have 5 degrees with like heavy rain for 4 days.
Not in the Sahel, for example.
Not in this?
Not in the Sahel, and not in many other
Maybe in the Sahel.
in Western North America, or in India, also in the Northwest. It's exactly the difference. It strengthens duration versus just winter, summer.
I agree. This is why we chose this. This is why we have all these locations, because we want to extend our understanding. If actually, because when I choose 200 locations around the world, I choose different rain, and we choose different evapotranspiration, right? And we choose different soil types, and we still get something consistent. Maybe it can be obviously not for all locations, but the majority of locations will show the same consistency. It doesn't matter if it's summer rain or winter rain.
I have a few other things that I would like to clarify. Do you really think you took 1 millimeter per day?
Above.
Do you think there is any recharge in 1 millimeter?
No.
So why is it above?
No, above.
Okay, 2 millimeters.
Because
no.
No, it can be 120 millimeter a day.
I understand. What I'm saying is there is a threshold. I understand there is a threshold from below it you don't get any recharge. Doesn't matter if you have evapotranspiration. It will go out before, but in your big data you include many events which do not produce, by definition, do not produce recharge. Am I correct, or am I totally?
Well, there is let's say there are linear functions where you say that you have the intercept, which is the threshold, right, of recharge, and then you have like the precipitation. So if you have above precipitation minus the intercept, this is the groundwater recharge. I know that it's for the mountain aquifer they did it, similar. Now, obviously, I do agree that there is some critical value. On the other hand, I did it like it's 400 years that you run. You take only the last 200 years, and then I don't know specifically which year will contribute more to the recharge. But because I wasn't interested in that, I was interested to see what will happen if it will shift. If the statistics will shift, how it will affect recharge. Obviously, there are years with more recharge and years without recharge. And which years will affect more recharge? It's not in the analysis. If I understood right, I'm not sure if.
One more question. In your model, or whatever models used, you apply the soil characteristic for a grid, probably 50 square kilometer, 20 square kilometer, depending on the database, the global database. Do you really think that if, let's go to Kriyat Gat.
Yeah.
Okay? You look at all the floodplain of Lachish and the top of the Les and the Nari and the Lis. The recharge is not across the entire landscape. The recharge is at points along the landscape. So how you get an average value for a grid that it's not working like that, just average.
The question is scale, obviously. And if in the scale, I don't know if they represent all the scale. I don't know that. But I'm not sure that diffusive recharge, I'm not sure that it's not everywhere. I think there is recharge everywhere. Yeah, because for example, even in Ramat Chovav, I took all the measurements of Elon, and I have a strong correlation between chloride and isotope, which indicate diffusive recharge even in a very arid region.
So to go to your colleague, the next door, Ofer, and ask him if recharge is everywhere. That's what he measured for the last 20 years?
Yeah, well, I was his former student. We still argue. but I think recharge, diffusive recharge occurs everywhere, I think. Maybe, yeah, if you know what, even in the Sahara, if you have intensive rain, in some sandy dunes, I'm sure that there is a recharge there. Like, not recharge, like deep drainage.
One quick question.
Yeah.
Is it the opposing effect, the different effects of rain and evapotranspiration in your conclusions are quite astonishing. Because you might expect that it's only a difference between them, and if one of them increases the same as the other one decreasing. Is it due to the fact that you some sort of infiltration speed is assumed so that the evapotranspiration takes place only below or above a certain depth in the ground? Or what exactly is happening with evapotranspiration? Because physically, once the drop gets below, I don't know, a meter or so, I would assume that it doesn't know how evapotranspiration.
Without plants, the rule of thumb is even...
That's an arid region, so there's
without plants, the rule of thumb would be like 20 to 30 centimeters, depending on the soil properties. But we included 200 locations with different soil properties. And the results again are consistent. So the soil properties might have some effect, but they have a limited effect because basically, once water passes the 30 centimeter, it depends when they pass it. If the soil can still evaporate water or not, but still, the soil, even with the variability of soil properties, we see the effect. So yes, we have to investigate that.
Sorry, I just see that there are many questions, and you can continue the discussion later because I want to give Tuvia the opportunity to give the 1 minute in Hebrew. Yeah.
Wow.
And just before you start, we do have our almost weekend today, and
we have everyone is invited as usual after the seminar for this weekly gathering, but today we have a special event for also for Amos. For everyone, again, it's open. You'll have a better kibud.
אוקיי.
טוב, טוביה, אז חוץ מאפרת ויהודה ונתן, אף אחד לא הבין שום דבר. אז יש לך עכשיו דקה אחת, 60 שניות להסביר בעברית ברורה, צחה ושווה לכל נפש. קדימה.
מה אני מסביר?
את ההרצאה שלך.
וואו.
קדימה.
לא הכנת אותו לזה?
לא, הכין אותי, אבל לא, חשבתי משהו אחר. בעברית?
בטח. בעברית צחה ושווה לכל נפש. אני מתחיל לך מההתחלה. אתה מתחיל עכשיו.
טוב, אז מודלים אקלימיים היום, אנחנו פחות יודעים, כל מודל אקלימי מראה שונות אחרת בתוך הגשם ובתוך האידוי. ההשפעה לא ברורה על המילוי חוזר לאקוויפרים, ולכן אנחנו צריכים לבדוק איזה קומפוננט בתוך הסטטיסטיקה משפיע על המילוי החוזר לאקוויפרים. בניתי מתודה שמאפשרת בנייה של מסדרות זמן של גשם ואידוי, ואחר כך גם יצרתי אפשרות לשנות את הסטטיסטיקה שלהם ולבדוק את הרגישות איך שינוי של הסטטיסטיקה משפיע על המילוי החוזר לאקוויפרים.
ומה קרה?
מה קרה? השינוי בממוצע של האידוי הוא הכי משמעותי באזורים צחיחים למחצה.
תודה רבה.
תודה. וואו.